which is this network and an initiative that we have going at UBC and internationally. It's been a lot of fun to take this very new research direction in addition to focusing on astronomy as well. And so I just want to share some of the questions and some of the problems that are facing our continued use of space. And by no means is this going to be exhaustive, but I wanted to try to give you a couple of different ideas for some of the problems that are out there. Now, to start this talk, like any good physicist, I want to start with cows. So let's go ahead and start with some cows. So understanding the current issue with space debris comes down to this idea of tragedy of the commons. And this is a fairly old idea, and it can be summarized by saying, all right, we have so many cows in a pasture. And that pasture is shared by, say, a village or so. And there are multiple farmers. And each farmer sees the potential for economic growth by adding one more cow. And that risk gets distributed among all other actors who are using that pasture. And they don't take into account that every other farmer is going to be thinking that, if I just add one more cow, then I can increase my economic growth. And so what actually ends up happening is that everyone starts adding cows and the pasture eventually gets depleted. And now in the kind of original version of this, there are a couple different things that are pointed out. One, there's no technical solution. So, if we get a little bit better at, maybe supplements that we give our cows or so forth, that you still have an issue with the amount that your cow needs to graze. And even if you're able to cut back on that, people will just add more cow. Hardin went further, so first this idea was kind of really popular, was written up kind of in this pamphlet with musings by Lloyd in 1833. And this idea has been around, before then even. But it was really popularized by Hardin in 1968 with this, I think it was in Science article that really started this ecological movement with tragedy of the commons. And Hardin went really far with it. And you have to kind of, when I see this quote, I imagine with some music in the background, it's a doom and gloom, and like someone saying that ruin is the destination toward which all men rush, each pursuing his own best interests in a society that believes in the freedom of the commons. Freedom in the commons brings ruin to all. Right? So Hardin's entire approach to this was that the state is the answer, that the state needs to come in and regulate for everyone, because no one can be trusted to regulate on their own. The economic interest is to always deplete or push the commons to a point in which you exhaust those resources. Now, there's been pushback on that idea, and in particular, there's this idea, the resilience of the commons, that once you actually start seeing the tragedy of the commons take place, that people can band together and be good stewards of the environment and actually push it back, maybe not to where it was before, but you could have it be a really productive area. You could prevent, whether it's pollution, overgrazing, overfishing, you can try to get back to, or you can try to prevent a lot of the negative effects that are associated with its use. But it's also possible that you just have total collapse of that commons. And so we've seen this in many different instances, and we have seen large collapses of fishing stocks, but then we've also seen people try to build some of those back in different areas. And so I don't want to get into all the different ways in which this could play out. But we do have examples of both some successes where we have resilience of the commons, but we also have certainly examples of the collapse of the commons. And often, when it comes down to it, it's really, there's not a technical issue that's involved. It's really a matter of will or the way society is behaving. It's also the case that it's not necessary for the state to completely step in. A lot of the success stories of resilience of the commons comes down to local groups who have just wanted to preserve their local environment and have been able to make changes, at least on a local scale. When you get to international, though, commons, you really do need states banding together and having a much more collective type of agreement in order to make headway. And you see that with maritime law as an example. So space. If we try to reflect on kind of how space came into the picture, it is interesting to think about, what was happening before Sputnik. And there were states, individual states, that were contending that their sovereignty went well into outer space. And so they were just extended upward. And it really was Sputnik that completely destroyed that idea. So, Sputnik was launched, it was overflying these areas. States were claiming to complain about it because there's nothing you could do, and it eventually became customary international law. States without saying no, you're infringing upon our territory without actually making that statement, they accepted the fact that a state can overfly their state without their permission. And so this led us to the space race, but it also made space a commons. So, immediately upon the launch of Sputnik, space became a commons. And so the way I'd like to kind of move forward is go back to cows and say, we really now have our new kind of pasture for our cattle. But when we started using space, the idea, there was the pervasive idea that space is essentially unlimited resource. And so the big sky paradigm was applied. And this big sky paradigm is an idea that was used in aviation. And it actually is very sensible, and it comes to, at least at face value, and that is only regulate what you need to regulate. And with aviation, it comes down to the sky is a big place, and the probability of two planes colliding is actually really small, except in congested areas. And so one of the things to do is to regulate more heavily the congested areas and then leave kind of some of the places away from, say, airports or what we call airways, much more free for use. And roughly that's what the aviation industry has used, and there are tragedies that are associated that have occurred, but it's been largely successful. And if you're not within a, very close to an airport and you're just flying around, there are actually overall few limitations on what you can and can't do. So the idea was that objects are unlikely to collide in space. And because they're unlikely to collide, let's not worry about regulating it whatsoever. And so what can go wrong? So I'm going to be coming back to this plot a few times, and actually a huge fraction of this talk is going to be just explaining what this is. So what we see is a cumulative number of objects versus time, where time is given in years. There's a total of payload, debris, and rocket body. By payload, you should think of this as your satellites. And I'm not making any distinction between what is active and what is inactive. It's just if it's a satellite, it's the orange curve. If it's debris apart from a spent rocket body or an inactive satellite, then it goes in green. And then the rocket bodies are then red. Now, these cumulative number of objects, these are only objects that are in the US Stratcom catalog. So these are objects that are typically 10 centimeters in size or larger, that have known orbits that are associated with particular types of events. So if it's debris, it's debris that is known to be associated with a particular event, for example. And this is a small fraction of the total amount of debris that's actually in space. One of the things that try to emphasize later, you know, the total number that we see here, there's incompleteness associated with it. So while this number, the blue curve, goes to 20,000 for objects that are 10 centimeters size or larger, it's probably closer to about 30,000 for 10 centimeter sizes or larger. And if you go down to 1 centimeter, which we can't catalog, people are able to look at it statistically, at least in LEO, using radar. But that's going to go up to almost 1 million for objects that are 1 centimeter size or larger. And to be very clear, if you have a 5 millimeter object going at orbital speeds, that can disrupt spacecraft subsystems and could cause entire disruption of the spacecraft itself. So this particular plot is full of lots of wiggles. Things are going down, things are going up. And so we have these sudden jumps. Those are associated with fragmentation events, events where suddenly a lot of debris is now put into the orbital domain. And at this point, we're not distinguishing where that debris is located. We're simply saying the debris is placed there. And so this is the 2007 Chinese ASAT test. What happened at that time is that one reason or another, the Chinese military decided that it was a good idea to blow up one of their own satellites in order to demonstrate military capabilities. And so they shot down one of their own weather satellites. Now this occurred at an altitude of about 800 kilometers, but that debris was spread out in a wide range of orbits, and a fraction of that depth of the debris actually crossed the International Space Station's orbit. It also is the largest debris generating event that we have on record. A few years later, there was an accidental collision. This was the Iridium-33 Cosmos 2251 tragedy. So here we have the Iridium constellation. Iridium-33 was active. Cosmos 2251 was a defunct Russian satellite, and they collided also close to 800 kilometers in altitude. This is extremely energetic. The collision hit at around 14 kilometers per second, and it spread debris over a fairly wide range in orbital space. The last bit that we see here, this sudden tick upwards, that's not actually debris. That's this kind of very poorly defined new space paradigm. And this is the accessibility of space. Notice that the number of payloads is jumping upward, while the number of rocket bodies, has a fairly constant slope. And so what's happening is we're getting better and better and better at launching more satellites at once. And no one demonstrates that quite as well as SpaceX. So I forgot to take the sound away from that. So just imagine it's aliens talking. Okay, so we have 60 satellites that are flat packed and then are launched all at once. And all of those satellites are now freely floating. They were just launched from the rocket, and they're going to disperse and go into their desired orbits. They'll later undergo maneuvers in order to put them into their intended locations for full operation. This is happening roughly every 2 weeks now. SpaceX is really changing the number of satellites that we see, and that is reflected quite dramatically in that cumulative plot. Now, in order to understand how a resource is being used, it's usually it's usually important to try to tally everything up. That's what that cumulative plot was trying to show, the historical tally of it. At any one snapshot, though, the common way of looking at this, its footprint, is to look at the satellite box score. And I believe, I'm not entirely sure if this is correct, but I believe that the reason it's called a box score is because it's a number that's always, or a series of numbers that are given in a small box in the quarterly orbital debris newsletter. I don't know if there's a different etymology for that, but I'm pretty sure that where it comes from. And so this was a box score from just a few days ago. And you can see that the current payload is about 5,646. There are a little bit more than half of that right now are active. So at least half of the satellites are defunct and are in fact space junk, many of which have no maneuvering capabilities whatsoever. So these really don't give us a sense of where everything is. And certainly, if we look at the debris number, this doesn't give us an idea of the origin of the debris or how it got there in the first place. The orbit breakup causes actually comes down to a lot of negligence. So almost half of all of the debris generating events, many of those upticks that you saw are due to propulsion related failures. So this is where one of those rocket bodies has unspent fuel in it and it explodes. And then it just sends debris everywhere. Delta II rockets are particularly fond of exploding, as well as, I believe, the upper stages of the Russian Soyuz or the Proton rockets. So you have these things that are generating quite a bit of debris. Batteries just occasionally explode. Unfortunately, it is the case, and this goes down to stewardship, nearly a quarter of the debris that we have in the catalog, again, this is just what's cataloged, comes from intentional destruction of a satellite. So the intentional deployment of debris, effectively. And then there's another quarter that's simply unknown. That's a so-called anomalous population. And at least a fraction of that is due to debris collisions itself, although that can't be verified, so we don't know. All right, what does the actual environment look like? So these are just the numbers, but it really doesn't give you a sense of how everything is located within the orbital environment. And so these are some screen grabs that I took from a program called AstriaGraph, which if you just Google AstriaGraph, it'll come up and you could plot whatever you want in terms of the distribution of space resident objects. So that's known bodies in orbit. And so right now I've taken a screen grab of the geo region. So this is the geosynchronous and geostationary orbits. So the orange is showing you the active satellites, most of which in this regime are in that thin belt, which are in the geostationary components, so where its orbit is the same as the rotation of the Earth, and so it remains fixed in the sky. But then there are also geosynchronous satellites that make figure eights in the sky, and those have an inclination associated with them. There's all this uncatalogued or uncategorized debris, and so it's known, but it doesn't have necessarily numbers associated with it, and it's not in the U.S. Stratcom database, so it's not included in that 20,000 that I was talking about. Look at the number of inactive satellites that are there. That's given in the cyan, and then there are also rocket bodies within this region. We can go to the medium Earth orbit, and this is where you have a lot of your navigation satellites. So this is where GPS is located, Galileo is located here, GLONASS, and then parts of Beidou, which is the Chinese navigation system, although a large fraction of Beidou is also in geosynchronous orbit. Look at the number of rocket bodies that are here. So medium Earth orbit has a rocket body problem. Oops, wrong way. And then if we add the uncategorized, there's a whole bunch of junk that's just, I mean, some people know what these origins are and so forth, but there's an incredible amount of junk here that's not directly associated with particular events and so forth. And there's, various people who are doing these cataloging are working on putting that in a catalog if it can be put in a catalog. I don't want you to think that all of the things that are uncategorized means that it's secret or something like that. It's just not in the, it's not followed within the published public catalogs. Okay, now to give a little bit more of an effect, we're going to take a fly from the medium Earth orbit regime, and this video is going to start by showing the some of the navigation satellites, and we're going to zoom in and take a look at low Earth orbit. And so you see the ring there, that's the geostationary satellites, and we're flying through here. And one of the things I want to impress upon you is that these things are all crisscrossing each other. So it's this beehive. Some of the satellites are orbiting in the same direction, but a lot of them are going in many different ways. And then this particular video just flies through the debris field for dramatic effect. So we'll go ahead and go through that.
So this is now kind of to scale, Aaron?
Yes.
Even though the previous ones were not. So, yeah.
Well, it's, you know, the satellites, of course, are all very small. And so it doesn't give you the full sense of how much space there is. So there's still an incredible amount of space associated in between every single one of these satellites. With that said, one of the things that I'll show in a moment, the density can actually be quite large for all of these. And as we kind of went through each one of those different parts, we were looking at kind of different zoomed in regions. So the previous one, the scale of the Earth wasn't right, but I think in the last one, the scale of Earth versus the orbital altitudes was probably roughly right. All right, so this big sky paradigm kind of set the stage that space is big, let's not bother to regulate it. I think it's really important to get an appreciation for how bad that was at first. So I'm just going to pick some highlights. So some of you might recall Starfish Prime. So this was an explosion that was detonated by the United States in 1962. And in the left image, that's the explosion as seen from Hawaii. So this was a 1.4 megaton nuclear weapon that was detonated at an altitude of 400 kilometers. It caused aurora-like emission. It changed produced some radiation belt structure. It caused an EMP that damaged some of the Hawaiian electrical grid. And these radiation belts critically damaged Telstar, the first communication satellite, and Ariel 1, the UK's first satellite. 4 other satellites were damaged by this particular event. So this was bad news. And this is one of the things that eventually led to the 1967 Outer Space Treaty, which I'll mention in a few more slides.
So Aaron, sorry to interrupt.
Go ahead.
Was that an accident or this was by design?
Oh no, this was a demonstration of military capability. So one thing to appreciate is the Russians and the United States were doing this. Nuclear weapons have been detonated in space purposefully. Russia did it. Then there was this nuclear weapons ban in space that went up, but then the typical type of state politics that you might expect. One said, oh, you're not adhering to this correctly, I'm going to pull out of it. Then the other person pulls out of it and people start nuking space again. So 1962, this happened after some fallout of that ban went into place and the United States decided to start nuking space again. So this is just one of the iterations of this. Now, there are still a handful of these, but I mean, it's certainly more than one. All right, so one of the first times astronomers got really upset about satellites was the Westford Needle Project, or Project Westford. So on the postage stamp on the left is showing you these Westford needles. And these were copper wires that were purposefully put in place in orbit by the United States military in an effort to create an artificial ionosphere. And so this was done as part of the Cold War effort, and it was because the ionosphere was too unpredictable or too unreliable to have guaranteed communications for very long distances. And so the thought was, if a ring of dipoles is just put around Earth, then you could use that ring as a reflector and bounce all your communications off that. And so this happened. 480 million copper wires were put into orbit, within about 3,500 kilometers. A first attempt occurred in 1961, and the dispersing mechanism didn't work, which is shown as a depiction on the right. And so what happened is there's a satellite that was supposed to disperse all of these copper needles, and there was an agent that kind of temporarily binded a bunch of the needles together, and then it threw them all out in clumps. And the idea was the exposure to radiation, solar radiation, would dissolve that, and then all the needles would disperse. But that didn't quite happen. So there were large chunks that were just sent out, and the dispersing mechanism failed. And so a lot of things went wrong with that. But in 1963, they were able to deploy that successfully, and a temporary ionosphere was created. And it was used for communications. It was very short-lived. It was very short-lived because it wasn't as reliable as what the U.S. military had hoped. But it's also the case that in 1962, the first communication satellites went up. So the entire need to dump that many dipoles into orbit was killed essentially before the project was even demonstrated to be possible because of new technology. So the communication satellites, eventually killed this project in part. But astronomers, radio astronomers, were up in arms about this particular project, and rightfully so, in my opinion. Select events, just to give you an idea of various things that have happened. So in 1968, there was the first successful ASAT, anti-satellite test, and this happened by taking Cosmos 249. So the Russians purposefully rendezvoused one of their satellites with another one of their satellites and blew it up upon command. So they turned one satellite into a kill vehicle and just destroyed another satellite. That generated a bunch of debris. In 1985, the United States successfully launched a missile from the F-15 and bullseyed one of their satellites. It's important to emphasize that everyone's blowing up their own satellites at this point. They're just demonstrating that they can, in case they feel they need to destroy space assets of an adversary. So in 1996, there was actually the first major collision in orbit, and this was accidental. So this was a French microsatellite collided with a fragment from a rocket body. And this is in 1986, when that rocket body with unspent fuel exploded, produced 500 pieces of trackable debris, and one of those pieces just took out another satellite. And so that's the first instance we have of that definitely happening. Going back a few years, but in a different class of problems, 1978 was the first use of the 1972 Liability Convention. I'm going to get to some of these conventions, I'll only briefly talk about them, but I'll mention that in a moment. And this is saying how people can be at fault in space, which is different how people can be at fault not in space. So Cosmos 954 re-entered and spread radioactive waste across Canada. And so the cleanup effort was about 6 million Canadian dollars, and Russia paid for 3 million of it. Another Russian satellite, a nuclear reactor, burned up over the South Atlantic near Ascension Island, and um, a week later or so, radioactive strontium was detected in some samples from Arkansas. So it is believed that that's part of the dispersal of the radioactive material into the upper atmosphere, and some of that made it all the way down into the weather system. And in 1979, there was the Skylab reentry with spread material across Australia. If we look at in space, we know that things are getting hit. We know debris is having an effect. Apart from those major collisions, there's lots of little things. And so the solar panels on the ISS are getting hit with things, and occasionally they break because they get hit by debris. Now, to be very clear, it's for some of these impacts, it is uncertain whether it was a meteoroid or whether it was orbital debris. At these altitudes, these are all very low Earth orbit altitudes, it's almost certainly orbital debris, but the micrometeoroid cannot be ruled out. So there's on the third panel from the left, there's a white speck, and that's a hole in the solar panels. So that was actually a sizable piece of debris that went through the solar panels. In the upper right, that's from the payload bay door of the Space Shuttle Atlantis, and so that's a fairly significant and energetic event. Down to the bottom left, that's a WIFPIC 2 radiator from the HST. It has over 685 impacts that are larger than 300 microns. And of course, is the glass in the cupola of the ISS that has been damaged by debris. All right, so people are behaving badly, but there is space law. So what does that space law address? Well, the 1967 Outer Space Treaty said that you can't own space, and it prevented the placement of nuclear weapons in space. So that's a very good thing. The rescue agreement made sure that every country who has the capability to help an astronaut will help an astronaut. A major success in international cooperation. The Liability Convention says that if it's your space asset and you damage something else with your space asset, you are liable. There's a registration convention and the Moon Agreement, which aren't so important for this conversation. One of the things that is not addressed in all of the international space law is the regulation of orbits. And so there's nothing that's actually saying where things can be placed or so forth, except in GEO. GEO is the one exception where the International Telecommunications Union can actually regulate both the orbits and the frequencies. If it's anywhere else, they only get to regulate the frequencies. And while you have to tell them what orbit you plan to put it in, you don't have to actually follow that. There are organizations that make recommendations for how debris to be handled, but I mean, they're really just recommendations. And individual nations can then decide to codify that into their domestic law, but it has some limited effect. So they specify kind of where you need to put things in graveyard orbit. So a graveyard orbit is where you stick a dead satellite that you don't want to destroy by deorbiting it into the atmosphere because it's too expensive to do so. There's the 25-year rule, which says at altitudes less than 2,000 kilometers, once a satellite is at its end of service, it has 25 years to deorbit. Again, it's a guideline. They're asking people to pacify, so this is getting rid of unspent fuel and so forth. All right. So, one of the dangers that we have of this unregulated environment is something known as the Kessler syndrome. And this is a situation in which we have the dominant debris generating mechanism is collisions with debris and satellites, or debris and debris. And it's an idea that's borrowed directly from planetary science. where they're looking at the collisional evolution of the small body population, such as asteroids and cometary material. The idea is, very simple. So you have some large body here, and it has some mass that's given by some, it's some dimension cubed, and its cross section goes as d squared. Then we could think of that body as made up of a bunch of other bodies, and if we are able to use up all of its volume, let's just imagine we can't, then we have the number going as that. And suddenly you blow that body up, and now you've taken all of that mass and you spread it out in more bodies, and your cross section is actually going up. So the number of bullets that you have to hit something, as well as the cross-sectional interaction between those, has all gone up as a result of taking one of those objects and breaking it apart. And so one of the big dangers in the orbital debris environment is that if you have satellites that collide, they take all of their mass and now they put into smaller components, and all those components get spread out and now increase the probability that you're going to have another collision within a certain amount of time. And that increased collision rate is another way of thinking of the Kessler syndrome. Of course, you can imagine space agencies have incredible interest in understanding the debris population, and so there are all these models that are being run. This is one of them by Liu and Johnson at the Orbital Debris Office for NASA. And what you see here is the cumulative number of objects greater than 10 centimeters. And this model was run prior to the Iridium Cosmos disaster. So this was just including the Chinese ASAT test. And the PMD is post-mission disposal. So if they have regular launches at the rate of 2009, we've increased since then. So if they're at the rate of 2009 and they have 90% post-mission disposal and no further mitigation efforts, then by 2030, certainly by 2050, you start to see this rise. And we're all familiar with COVID-19 of looking at exponentials and how flat exponentials look when they start. You're seeing this runaway growth of debris, and that was with just the debris field in 2009. If there's active debris removal, depending on when you actually start that active debris removal, you can significantly reduce that growth rate. And so in this paper, they, which is often cited as the modern Kessler syndrome papers, they note that right now, in order to prevent a runaway, we're going to have to start actively deorbiting the junk that we're putting up there. All right, let's take a look at some numbers here. So we can think about the collision rate as just being the number density in a given orbital shell. We can take the collisional cross-section for our object of interest. So this will just be our satellite's cross-section. And then we could take a typical velocity in a given shell. Now, that V is really going to be part of a distribution function of velocities, but I'm going to go ahead and just use the orbital velocity there. And I'm going to justify that by saying, remember that video I showed you where all those orbits are crisscrossing each other. This approximation that the typical speed is going to be the orbital speed is probably not that bad. We can next define this optical depth-like term, which I give here as tau, which is just going to be that collision probability over some time period. Now, this is the Poisson process, and so the probability that there's no collision in delta t is just going to be given by that optical depth and exponential, just as we're used to thinking about optical depths as astronomers. And then the probability that there is a collision is going to be 1 minus that. So here's the distribution of objects in Earth orbit from the catalog as of late March. What I'm showing is a semi-major axis, but note I'm giving this an altitude. So if you want to know the true semi-major axis, you have to add the radius of the Earth to that. And this is the number in 5-kilometer altitude bins. And I've already said a couple times that those numbers that we give do not really represent how the material is distributed in about the system, and that's really emphasized here. So you have these spikes, and that's because they're preferred locations for satellites. They're preferred locations because satellites have jobs, they have missions. They need to do things like observe certain parts of Earth at the same time every day. They need to have certain communication constraints, so forth. And so there are these spots where people prefer to put them, and that's shown here. So the green histogram is showing where these different satellites are parked. The debris is spread out over a large area because it actually evolves. One thing that I do want to point out, the spent rocket stages are fairly spread out, except just below 1,000 kilometers. And there's this spent rocket stage cluster that people are actually really worried about for the future collisional evolution, because the school buses, which can't be steered anymore, and given enough time, they're going to start colliding. But these are semi-major axes, so this really doesn't give you the full idea of what the distribution of material is like. And so for that, I reconstruct the number density, and all I've done is I've taken those, and I know what the orbits are for every single one of those bodies. So I just average kind of their numbers over their orbit. And so they get a higher contribution at epicenter than at the pericenter, for example. But I do that, and now I can reconstruct this. I still have these spikes from the satellites, but a lot of material is more spread out. In fact, the rocket body cluster that I just pointed out is much more spread out, and that's because those are on very eccentric orbits. But still, you have this spike that's just above 750 and one around 500 or so. These are areas in which people like to put satellites because they're very good for sun-synchronous orbits, for example. Now we can go ahead and take that, and I could just ask, what is the collision risk for one object? So I'm going to calculate what that tau is. And I use something like a cross-section of 10 meters squared or so, which once you add solar panels into the mix, that's not a bad approximation. And so what we have here are numbers that, particularly within these satellite clusters, that are around 10 to the minus 4 or so in the optical depth after 1 year. So for any given object, the risk of a collision among these known objects remains small right now. But this is, you have to factor in that this is for every object, and every other object has that risk. And so you're going to get then a factor of 100 or so, or a factor of a few hundred within that tau. And so the probability of actually having a collision is moderately high, where every decade or so you should be expecting to have a collision. Now, whether that happens or not also depends on how good we are at steering satellites and so forth. But a lot of the satellites are dead. I'm gonna, skip that slide here. There's one more thing I want to at least get to the production and the removal of debris. I don't have enough time to go through everything that I put into this talk. So whether the Kessler syndrome develops does depend on the clearing mechanisms. And so it's going to depend on whether the rates of the collisions plus the introduction of new material plus the introduction of spontaneous fragmentation, like rockets blowing up, if that is greater than the clearing mechanisms plus active debris removal, then we have a problem. Because now we're just going to get to this point where eventually things are going to cascade, and you're going to turn everything into space, into orbit, into rubble. So what are the clearing mechanisms? You have gas drag, radiation pressure, and resonant perturbations. Those are the big three. So for gas drag, this is most important below about 1,000 kilometers, where the atmosphere really matters. And it's actually really fairly simple to describe it. You just have the drag, which is given by by hydrodynamics. Now, CD is a coefficient that does depend on things like the velocity of the object and the current density, but it's for most of the conditions that are that are in the low Earth orbit, it's going to be a factor of 1 to a few. Rho there is the atmospheric density at the current altitude. A is the effective area of the satellite, and then V squared is the relative motion of the satellite through the gas. And so what I'm showing on the right is then the decay time for different area to mass ratios. So it's not the mass of the satellite, it's not the area of the satellite, it's the area to mass ratio of the satellite that matters for its deorbit timescale. So you often just parameterize everything by this mass to area. Oops, no, area to mass. So that dash line is 25 years. And so if you go back to when I was talking about guidelines, you have that 25-year rule saying that if we're going to just let things passively fall into Earth, after 25 years, how high can I stick it? Where if it has an area to mass ratios of 1/100th of a meter squared per kilogram, then I can only stick it at altitudes of about 650 kilometers and lower if I'm going to be compliant with that guideline. Where if I have a much more draggy type of satellite, a large area to mass ratio, maybe I could go to 800 kilometers. But this gives you a rough idea of the timescales that are involved with deorbiting. And those wiggles that you see, that's due to the solar cycle. So the atmosphere is actually changing its density along with the solar cycle, as well as the scale height and so forth. And that's reflected when you do these drag calculations. And I want to give a shout out to Katie Rink, who worked with me as independent studies where we were playing around with some of these models so we could do some of these calculations ourselves. Radiation pressure will also perturb satellites. And so on the left here is just an idea. Now this particular diagram was written in the context of dust maybe orbiting a planet like in a ring, but for satellites it works equally well. So you have an object that's going about the planet, and then you have the sun, which is sending photons out. Those photons hit the satellite and impart momentum onto it. And we could describe what that's like. And one of the interesting things that to keep in mind is that the radiation pressure can actually significantly extend debris removal regimes well above that 1,000-kilometer regime in which gas drag will naturally act. And so the Westford needles were an example of that. And so the US military pushed back on everyone and said, no, these things are going to disperse and they're going to be removed in a decade because of radiation pressure. And the way that works is you make the orbit very eccentric until it eventually has a parity that drops low enough that atmospheric drag just brings it down and removes it. And that's largely been true. Most of the Westford needles are gone now. However, there were clumps that never dispersed. And so there are these large clumps of needles that are still in orbit around 3,500 kilometers that just you can't do anything about because radiation pressure is not effective on them, or is ineffective. The final thing I do want to bring out is this, this clearing mechanism through resonances. And that is you have the Earth is oblate. The Earth is, and even on top of that, has lots of perturbations, which create lots of gravity perturbations. And that's what's shown at the bottom. There are all these different variations in the potential height of the Earth. You have the moon and you have the sun creating perturbations. And you can have resonances that are between the precession frequencies of satellites and some of the natural frequencies that are associated with these perturbers. And as a result of that, you have this web of res structure that goes through our satellites. And that's what's shown here. That's some nice work by Aaron Rosengren. And what's evolved are orbits of two hypothetical Galileo satellites. And you're seeing the color of the dots represent the years into the integration. For the top panel here, this particular initial condition, which is just varied by the location of the node at the start of the simulation, gets bounced around all over the place. Without active station keeping, all of the navigation satellites would be all over the place. They're in unstable orbits, and they have to have active station keeping in order to keep them where they are. But if you can imagine designing a mission where you purposefully place a satellite on one of these resonances at the end of its lifetime, and maybe that's much cheaper than than forcing the satellite to deorbit into an atmosphere, or maybe it's much cheaper than putting it into a graveyard, or it's certainly going to be better than a graveyard orbit in many cases. And so you could get these resonances to do the job that solar radiation pressure did for the Westford Needles. All right, now I've gone I'm toward the end of the time that I have, so there are a couple things that I just want to point out. So one here, so we can actually see the creative process of time. So I talked about the iridium cosmos debris in the Fengyun 1C. Fengyun 1C is the Chinese ASAT test debris. So this is the fraction of debris that's deorbited as a function of time based on just the material that's in the catalogs. And so we can actually see this material deorbit, and we have an idea of what that rate is. And then we can understand how long some of the material will be in orbit, although it does depend on some unknowns like the area to mass ratio. The stepping that you see, that's the solar cycle that's going in. So that's why it's shallow at first and it goes higher and then it's shallow again. All right. So there's a lot of stuff that I could talk about here. I'm just not going to. One of the things that I do want to talk about is facing the consequences of our ambition. So we have a lot of stuff that's going on, and we're rapidly changing our use of space. So this is a video that was put together by the company AIG, and it's only going to show satellites that either have gone into orbit since 2017 or are proposed to go into orbit. So this is going to show mainly the consequences of the mega-constellations. So, oops, no, stop it. What did I do? Oh, I clicked on that. Okay, good, stop laughing at me now. There we go. So 2017, there were just some globe stars that were put up there. 2018, exact view and iridium were added. Now, 2019, you start to see SpaceX, and 2020, this is if SpaceX, OneWeb, and all these other places are putting satellites up at the timescales or on the timescales that they propose to put them up. And there are actually a very large number of these. So currently we have 5,000, roughly, almost 6,000 now, satellites in orbit. As proposed, when you put all these together, that number is going to go up to about 50,000. And these are 50,000 satellites on very particular orbits. So as long as all of their station keeping works and there are no disasters, there are no fragmentation events, there are no accidents, everything's going to work fine. But as soon as you start having one of those accidents, as soon as things start going wrong, there's the possibility of it very rapidly precipitating out of control. So if I just go to the FCC filings, and let me tell you, that's an adventure going through those. But if you go to the FCC filings and you start extracting some of these, as I did for SpaceX, OneWeb, and Telesat, we can go ahead and plot what their semi-major axis altitude is. And these things are designed to be at these very specific altitudes. And in fact, within that chunk there, around 300 kilometers, there are actually 3 separate bands, very separated by only a little bit. If I go ahead and use that to calculate a 1-year optical depth, assuming that all of the orbital nodes are mixed, then these collision rates here are just huge. So it's good. Within a year, you're going to have these things just turn into total debris shells. That's assuming the orbital nodes are mixed. So as long as you have strong station keeping, then these probabilities go way, way, way down. But if there's something that really goes wrong up there, it can get out of hand. And so the box score number that we talked about, The cumulative debris plot that we talked about, that's really not the right way to be thinking about the orbital debris problem. The orbital debris problem is, what is the collision risk at that altitude? And that's how we need to be talking about it as we move forward. Now, I'm totally out of time here because I just blew through all of that. There are good things that are happening, absolutely. Let me just show you one video, and then I'll end from there. There are all these implications for, Okay, so the good things that are happening are that, everyone is getting afraid of debris, including militaries, because they're realizing that they can't control the debris once it gets up there. There is a push to rethink guidelines. People are getting involved, just citizen science, where there are now apps that you can get to help you track satellites and do observations of what's happening. That won't help you with debris, but you can at least track the satellites themselves. And there's just a greater public awareness of the issue, which then puts pressure back on the politicians. So one thing that is of particular interest is these investments in debris removal and mitigation technology. And I'm going to just show this quick video, which shows 3 different ideas. So one is to use nets that can capture debris. So you'd have to first rendezvous with something and capture it. Another one is to use a harpoon and capture it that way. This harpoon is designed to prevent fragmentation, although I still think that's a little risky. The other one is to end your mission and extend the capability and really increase your area to mass ratios to use these sails. And those sails will cause things to rapidly deorbit. Now, the net has already been tested in space. So this is from one of those missions where they launched their own debris and they recaptured it again using one of these nets. There's the harpoon experiment, which pretty much looks exactly as you would expect based on that previous video. This is the same company. And so they're going to fire a harpoon at this. And so they'd be able to capture a spacecraft like that if they hit it right. There's also advances that are coming in with orbital servicing, and we've recently seen some details with that. And let me just go here with the very last slide. So, so there is technology that's being developed that's going to help with all of this. But again, the tragedy of the commons is not a technical solution, at least by itself. But then we go to higher density orbits like are proposed for the mega constellations. We could have the active debris removal, which is what we just saw. And then anytime you start adding things to a satellite in order to make it deorbit rapidly or to force it to go into particular orbits, that increases the cost, and that changes the equation on how people actually comply. And so we have a lot of technical solutions for tackling the orbital debris problem, but there has to be a policy solution that is included, else it won't work. And that's where I'll end.
Hey, thanks, Aaron.